Okay, our next speaker is Yuan Miao from the University of Amsterdam. Please, Yuan.
Okay, thank you very much. And first of all, I'd like to thank the organizers for giving me such a great opportunity to present my recent work. And my name is Yuan Miao, and I work at the University of Amsterdam. And today I'm going to talk about the Q operator and the spectrum of spin 1/2 XXE model. And this work has been done in collaboration with my supervisor, Jean-Sébastien Coe, and Jules Lammers from Melbourne, and Vincent Pasquier in Saclay. Yes, so first of all, I'd like to motivate ourselves why we're interested in the problem of the spectrum. So basically, if we know a complete spectrum, namely all the eigenstates of a quantum many-body system, first thing we can do is we can, for example, study the density matrix, which in turn can tell us about the entanglement entropy or the thermalization in a closed quantum system. And furthermore, if we know all the eigenstates, we can also study out of equilibrium physics, such as a quantum quench, which is we start with some initial state, which is not eigenstate of the Hamiltonian, and study the time evolution. And furthermore, we can also study, for example, some correlation function and how does it evolve with time. And this in principle also related to the defect in the gauge theories. And if you say, okay, let's talk about classical models, and indeed this also closely related to the partition functions of some classical vertex model. And there we would like to know indeed all the eigenvalues and the eigenstates of eigenvectors of the transfer matrices, which in turn we need to know the spectrum. And the model that I study is a quantum XXE spin chain. It's quite simple. So there's just one-dimensional model with spin 1/2 on each side, and they interact only with the nearest neighbor. And here there's a parameter anisotropy parameter delta, and we have three regimes with respect to this delta, and they are distinguished by the properties of its antiferromagnetic ground state. So they're gapped, isotropic, and gapless regime. And today I mainly focus on the gapless regime. And in the gapless regime, there's still some special points, which is called root of unity. And they are basically a different way to parameterize this delta in terms of this eta here. And when eta is I pi times some rational number, where L1, L2 are co-primes, then we are at root of unity. For example, if eta is I pi over 3, then delta is 1/2. This is at root of unity. And why this is special is that basically the underlying quantum group structure will become different from a generic eta, and there we indeed find additional degeneracy, as we will see in a moment. And the traditional way to solve this Hamiltonian is to solve it via beta ansatz. And here, basically, this is a set of coupled equations called beta equations. And the solution to this beta equation is called beta roots. And the beta roots, we can use algebra beta ansatz to reconstruct the eigenvalues of transfer matrices and all the eigenvectors such that we obtain the spectrum. And one of the questions, of course, we would like to ask ourselves is whether the beta equations are enough. And indeed, at root of unity, there are some problem. So namely, if we consider a solution with such a configuration of a bound state, which is called exact strain, or also I referred as Fabricius-McCoy strain. For example, if L2 is 5, then basically they are the bound state that locate in the spectral space like that, with each of them differs by I pi over 5. And the problem there is that if we consider it as a bound state, then the scattering phase between this bound state and all other beta roots are basically trivially 1, and it carries no local conserved charges. And basically, it means that if you already have a solution to beta equation, you can in principle add this bound state, and it will not modify other roots, which basically means if you try to solve this, you will not find any physical solutions with those Fabricius-McCoy strains. And indeed, there's a way to solve it. Namely, we consider object, which I call a two-parameter transfer matrix. So the transfer matrix is, again, defined as usual. So there are this Lux operator that attach to each physical site. And in the end, we trace over the auxiliary space to get the transfer matrix. And if you want, the explicit expression can be written in terms like that. And what's important here is for this XXE model, the auxiliary space they are just representations of UQSL2 algebra. And basically, it means that this algebraic structure are Q-deformed. And it permits an infinite dimensional complex spin representation. And what we have proven is that indeed there's a factorization of this Lax operator. That so now we have U and S, both are complex, and we can combine it into X and Y, and indeed they factorize. And furthermore, we can use it to show that so this TS Highsmith is auxiliary space with this representation can be written as a two operator multiplied with each other and they commute. And furthermore, they are just the Baxter's Q operator. And this can be easily seen considering the decomposition of the representation in the auxiliary space. So this infinite dimensional representation can be decomposed into a finite dimensional one and another infinite dimensional one when S is half integers. And with this decomposition, we can easily derive the Wronskian relation. And also we can show that the Q and P satisfy matrix TQ relation. And also fusion relation, we can get it for free. By this step, everything, all this anisotropy is generic. But at root of unity, there are further simplification, namely when eta is at root of unity, there's another decomposition for any complex spin S, which is L2 dimensional. And similar things happened as before. And furthermore, this T tilde S is basically auxiliary space with L2 dimensional. And we can show that we can also factorize it into Q and P. And this Q and P, again, they are Q operators. And they are basically proportional to this infinite dimensional auxiliary space one. And using this, we proved some conjecture that has been conjectured before by Kolf and Luca et al. It's called, we call it truncated fusion Wronskian relations. And this basically means that we can really construct this T tilde S, let's say using computer very easily, and we can diagonalize it, even study the eigenvalues analytically. And which means there's no problem with this exact string that we have. And I'll show just one example of this problem. For instance, if you consider 12 side with delta 1/2 and 0 twist, basically these tower structure are all the states that have degenerate eigenvalues in TS, which here is just auxiliary space of 2S plus 1 dimensional. So this usually you get from fusion. However, these states, if you naively put back in the beta equations, you will get basically, you cannot solve all these beta roots. But indeed, since they are not degenerating this T tilde S, thus the Q operators, we can just find all the eigenvalues. And indeed, analytically, for example, we start with the pseudo vacuum. Then this bottom of the tower is the one beyond the equator, which namely all spin down. And indeed, it consists of 4 of these Fabricius, McCoy, or exact strings. And analytically, they are just polynomials in terms of exponential of this U. And furthermore, we have proven that all these bound state within this tower, they are like free fermions. So namely, we can add or subtract them. They are still eigenstates of the transfer matrices. And with this, we basically conclude here is that we have solved the problem with the spectrum of x-axis spin change to unity, and we found these descendant tower structures which have not been reported before, and we have proven some new relations with the fusion and Wronskian relations, and the one possible extension is to study the spin 1 generalization, which has been studied in this paper by Vernier et al. And moreover, it seems like this structure has some kind of generalization of Onzaga algebra, which hasn't been studied thoroughly yet. And we also have some results about thermodynamic limit, which I don't have time to explain. But if you're interested, you can ask me. I will try to explain. And hopefully it will appear next week in the archive. And the end, I would like to thank my collaborators again at around the world. Yeah, so it's really the project started at the beginning of the pandemics, which actually is helpful in some sense. And the most important thing is to thank you all for your attention. Thanks.
Okay, thank you very much. Questions?
Okay, I could begin. So if you just deform your model a little bit by, I don't know, introducing homogeneities or going slightly away from this special point, normally I wouldn't expect there will be any problems with incompleteness of bit ansatz, right? And another point is that in addition to your bit ansatz equation, you can also consider the dualized bit ansatz equation. And then normally if you combine the information from two, normally it's fills all the gaps.
Yes, so basically, as you said, indeed, you can try to get away from, so you can, the easiest thing to do, as you said, you can put in homogeneity, which doesn't change any at all of our result. But you can also do something even simpler just by putting a small twist.
Yes.
And indeed, what you can observe is that these bound states start to split. So they are kind of, for example, here we have this bound state, it will split into two bound states. And there, everything again is regular and you can solve everything. But what we really aim to do is whether we can analytically just to find it with some, let's say, zero twist or some special twist where these solutions are possible. Yeah.
Thank you. But as I said, so if you consider a second well, I'm not sure here. But okay, so any other questions?
Can you build the eigenvectors corresponding to this?
Yes. So yeah. So okay. Since we know the operator itself, we of course know the eigenvectors, all the eigenvectors actually. But then there's another question: is whether we can build it from something like algebraic beta ansatz, which we are still working on it. But there are some results in the paper by Vanier and collaborators where they really write down the operator that kind of create those exact strings. Yeah.
Other questions?
Yeah, sure. I can follow that up if that's okay.
Yeah, sure.
Yeah. So yeah, there's that one special case that we studied that there's this algebra. Do you see? I'm not sure precisely what you meant in this quick thing you wrote on the last slide. Is it that there's a generalization of the algebra, or is it the same algebra that applies to a more general model?
Yeah. Okay. Maybe I wouldn't say it. Okay. Maybe it's more like a generalized. Let's say there may be some hidden Onzaga algebra. But I mean, that's my suspicion. But
okay.
Yeah.
Okay, but do you have any other sort of special points where you see something simple happens, and then one might hope that there's an algebra that's explaining these degeneracies that's simple to understand?
Yeah, so it's more or less along your paper. I mean, basically, I'm trying to at the moment. I'm trying to find all the operators that really generate those eigenvectors from, let's say, from a parent state or as some descendant, and these operators probably among themselves satisfy some sort of Onzaga algebra. That's my
okay, but it won't be exactly the same. It'll be some kind of modified version.
It will not have the nice locality properties that you in your paper,
okay.
for example.
So it really will be more.
Yeah, it probably looks a bit more ugly, but yeah.
Okay, but nicer than Fabricius and McCoy, I hope, or.
Yeah, so basically, from this example already, we have shown that because previously people used this loop algebra to study this degeneracy, and if you sum over them, which you get exponentially many, this already couldn't be achieved via the loop algebra. And furthermore, the loop algebra commute with at some certain magnetization commute with the TS, but doesn't commute with T tilde S, which is the Q operator. So it's not really the best way to look from this point of view. So basically, I think maybe there are better ways to find, to solve this problem, not to use any of this loop algebra.
Good. All right. Well, that's real progress. Good. Thanks.
Yeah, no problem.
Are there any more questions? I wanted to ask you about the thermodynamics. you mentioned at the end, but I guess we can discuss later. But if you want to say something about.
Sure. So basically, as you can see, it's easier to construct everything in a finite chain, and we get really nice results and so on.
Okay. We'll discuss later.
Yeah, we can discuss that later. Yeah, thanks.
Rules are rules, you know.